Garcia, and I'm going to present the synthesis of dihydroamino acid containing peptides as inhibitors of aggregation. But let's start talking about tau protein. Tau protein is a protein that everyone has in the brain. It's a brain protein which function is to stabilize the internal structure of the cell, allowing them to interact with other cells. So this is a really important thing about this because PHF6, the molecule that I'm presenting here, is a hexapeptide segment of this protein. This protein, as I mentioned before, in a normal brain, it has the function to stabilize the inner structure of the neurons. But what happens when the abnormal function of tau protein is affected? When we have an abnormal function of tau protein, we can see the folding states or these kind of clumps called neurofibrillary tangles. These neurofibrillary tangles are characteristic of dementia disease as Alzheimer. It has been found that PHF6, this hexapeptide region of tau protein, play an interesting and key role in the disassembly of these monomers or these clumps of tau protein. So using PHF6 as a kind of candidate or as a protocol to follow about how to create like the disruption of these monomers, in 2017, Segal and co-workers, they decided to test this PHF6. What they did do is, you can see here we have 6 amino acids, right? In each amino acid, they changed a proline. And they saw that at position 2 and 3, they have like the best stability. And no, it's not about stability. They saw that the disruption of the previous tangles was promoted. And also, they saw that it wasn't forming like the beta sheet formation in the protein. So that helped a lot to understand better how this dementia disease works. Considering that, we decided to work with the dihydroamino acids. And I'm going to explain why. Proline is the most rigid amino acid. Proline doesn't have a hydrogen here. So we avoid the hydrogen bonding interaction with other molecules, doing like this, that the beta sheet formation is not like performed. And the third thing is this is more rigid, as I mentioned, and it like promotes the C-turn, like we can see here. Dihydroamino acids share some of those properties. Dihydroamino acids, you can see they are rigid structures because we have this double bond. That is helping to the peptide to keep in this like linear form, or it can promote the C-turn form. Also, we have the allelic 1,3 stability that is restrain the flexibility in the peptides, and we have discovered in previous studies that the dihydroamino acids show more stability against proteases or these enzymes. So that means that they live longer than other peptides. Considering that, we want to insert these amino acids, creating these 4 analogs. They are called T2, T3, V2, and V3 because the number is because of the position that they were substituted and the amino acid that we use to create this dihydroamino acid. T2 is for threonine, that is like the threonine dehydrated. It's called dihydroABU. It's a medium-sized dihydroamino acid. And V2, they come from valine for beta-hydroxyvaline. And this is a bulky size amino acid because we have these 2 methyl here. So having that, we were testing our hypothesis and we started to the synthesis of these ones. For that, we decided to use building blocks. These building blocks are allele-protected amino acids. From all the protecting groups that we have for the amino acid in the NH terminus, allele 1 was the one that performed better results. And then we need beta-hydroxyamino acids. Why beta-hydroxyamino acids? Because in order to create to insert a dihydroamino acid, we have some techniques that they involve the dehydration of the molecule of the peptide. That's why we have a hydroxyl group at the beta position of the molecule. Threonine, I already have an OH, so we shouldn't do anything. That was fine. But in the case of the beta-hydroxyvaline, we have to synthesize this one, getting this OH at the beta position in this amino acid, so we could do the next step. Considering that we have our alloc amino acids and our beta-hydroxyamino acids, we started to do the synthesis of these analogs. Let's be honest, at the beginning we thought that we could find one methodology that it could help us to create all the analogs, and it didn't work in that way. But that led us to something good. We are presenting 4 different ways to insert the dihydroamino acids. Some of them, they were better than the others, but it was like a learning process thing. we wish that we could do like the same synthetic pathway, but we are gonna see how they are changing. So for example, I'm gonna explain the substitution at position 2. The substitution at position 2 involves two techniques: solution phase synthesis and solution peptide synthesis. Solid peptide synthesis. So in this one, what are we doing? We have the alloc protected amino acid in the NH terminus, and we have our beta hydroxy amino acid. From conditions of a normal coupling, we just do the dipeptide, and then in this dipeptide, we perform a hydrolysis. Why a hydrolysis? Because we want this carboxylic acid and this alcohol here. It's well known in chemistry that when you have a carboxylic acid and alcohol, you can perform an aslactone. And the aslactone is the key reaction that we are gonna show. Because once that we have this aslactone formation, we are gonna perform the key reaction, the aslactone ring opening. This tetrapeptide, that is the last part of these peptides that we have been synthesizing, it was done by solid phase peptide synthesis. And this was just done in the synthesizer. We just load amino acids, we receive this thing, and after having these amino acids all protected, we just perform this key reaction with DMAP and NMP. This reaction takes around 2 days, sometimes 3. In once that we open this aslactone, we lose this molecule of water, and we get the insertion of the dihydroamino acid in the second position with all the amino acids still there, but they are still attached to the resin. So what we do, we perform change of the protected group here, because you remember that PHF6 has an acetic group instead of an allo group. So we remove the allo group, we put an acetic group, and we have total cleavage to get the analogs that we desire. So in this case, we get V2 and T2. In the case of T3, we are doing something different. We didn't use solid phase peptide synthesis. We synthesize the tripeptides from the last part. So we just do couplings and removal of the CDC group by hydrogenation. Once that we had the third part, we use different for V3. For V3, we create same process, we create the aslactone, and once that we have the aslactone, we couple it with the tripeptide that we created, all in solution. We have the deprotection of the groups, the acetylation in this case with the amino acid at the beginning, and then because we have an ester here, we just change to amide, total cleavage, and we have V3 in really good yields, comparing with the other ones. But for T3, it didn't work in that way. So what we do, we use amino acid, bad amino acid, until we got to this key reaction. Then when we have the pentapeptide, with the beta hydroxy amino acid inserted, we just perform a dehydration. And the dehydration is giving us like the product that we already expected, like the Z1. Once that we have this dehydration, we just attach the attach the last amino acid, and we do with the total cleavage. Finally, we have got the 4 analogs of these amino acids. You can see small quantities, but they are enough to send them to our collaborators, because we are sending them to the University of Medicine in Nebraska. In Nebraska. And we are gonna expect that they can do like the essays to see if they are like the conformation that they have. And we are doing the proteolysis too, so the characterization in order to publish. We have finished the synthesis, and now we are just waiting to identify them in NMR to see that we already have those ones in the pure quantities that we want. I just want to acknowledge my advisor, Stephen Castle, and all the people who have been working during these years trying to get these amino acids, this peptide dehydrated. Logan, Judy, Joshua, Josh Penn, and the team in the University of Nebraska, the Medical Center, that they are now working with these samples to see if they really disrupt aggregation and what is the conformation that they have. And I'm happy to take any questions about this project.
So back on when, oh my gosh, I'm trying to remember what you were doing. You were using osmium tetraoxide to add, there was an amine, a protection amine, and an alcohol. Oh yes, so like from 5 to 6, yeah, on the bottom. Did you do that reaction?
No, so this reaction, I did it once just because the osmium tetroxide is hard to handle for undergraduates, so I just was there to help them. This is called beta amino hydroxylation. So what we're again wanted is to have like the amine in this position and the OH in this position, like they're attached to like adjacent carbons. So this reaction is not really challenging. It's a reaction that it has been done before. You just have to be careful because of the osmium tetroxide is pretty toxic and you can get blind. And we don't want that. But yeah, I have been done the purification of this product. But these are a pretty nice reaction.
Any other question?
What, can you go to the table that you showed right at the end?
Sure. Oh, sorry.
So are these all compounds that you guys have made in your lab?
Yeah, I have made them.
All of these?
Yeah, so for example, pH of 6, P2 and P3, these are the controls. We made it by solid.
But they've been made before, yeah.
Yeah, these three, they have been made before. This is the one that we have the hexapeptide for tau protein in the brain. So, because they don't have any different amino acid, it's just a linear chain, it can be done by solid phase, like, pretty
Yes.
easily. These are the ones that stick out and coworkers thought, and because we are comparing like the stability, and we are comparing like the structure, we synthesize them to do like all the analysis with them. But yeah, we did them in the lab too, but they are not challenging at all.
Okay.
Can you go back to, I don't know what slide, this is like where you are opening up the laptop?
The vectoring happening.
Yeah, so you mentioned you're gonna kick out water, right? What's the mechanism?
Yeah.
I just wondering.
I'm glad that you added this one because I put so much effort trying to do the vectoring happening. So this is the mechanism that we have. One of the, as I mentioned, we are using a base step. In this case, that we are using this. This is the base that we are using, and then it is just attacking in this carbonyl. We are having like this intermediate structure that we have in the charts that they are like balancing the equation in the chemistry. And once that we are having like this this bond is breaking because of the double bond, it's coming back by resonance, that is a driving force, and we are having this negative charge here by resonance again. This is like the ones that is like pulling this nitrogen to take this, like the hydrogen that we have there. I really like this structure because at the beginning it was really hard for me to understand how it was working, using like these two molecules. But in reality, it's like it's simple that it shows. The problem is like the molecule that is like in this case the amine that is coming here to interact in this part. It's like a tetrapeptide, so it's more hindered than we have like a simple amine with a methyl group here. So that's something that it could avoid, like, or it can be like have obstacle in the insertion, like of getting better views.
So that's why this method doesn't work for medicine.
Yeah, it's because in this one, like one that we have here is like a glutamine that is protected with a trityl group. I don't know if I pronounce it right, guys, but it's TRT group, and that's like huge. So that's the thing that probably is avoiding us to get like that substitution 3 and instead of a substitution 2, because substitution 2 has failures. But they are like hindered, but not as bad as the other one.
Okay, thank you.